Okay, before we get started with the tutorial for today, we do have a couple of announcements. So the first one is that yesterday there were updates to the Rubin Science platform. Small updates happen every Thursday, as you know, during the patch window, but yesterday there was some bigger changes happened. So the details are available in 2 announcements that were posted to the Rubin Community Forum. It's in the science category and in the data preview category within science. So you know right where to find them. And the 2 announcements, the 2 big changes, one, truth tables are now available. So in the documentation at DP0.2.lsst.io, there's more information about the contents, and you will also find a new notebook. It's called 08 truth tables.ipynb. And it's got a little demonstration of just what the contents are and how to join them together and how to join them with the objects catalog. So these truth tables have been matched to the objects catalog, which remember is detections in the deep coads. So very similar to what was available for DP0.1, but now matched to the new DP0.2 object catalog. The second announcement is that your notebooks/tutorial notebooks directory can now be made read-only very easily, and it can stay that way. And if you choose this option, which is highly recommended, it means that you will always have the most up-to-date versions of the tutorial notebooks without having to do anything. So there are instructions in this forum post about the permission changes for your notebook/tutorial notebooks directory. The easiest way, and if you don't need to save the changes in the tutorial notebooks directory, just use your terminal to cd into the notebooks directory, fully remove tutorial notebooks, just rm-rf it, get rid of it completely, log all the way out, log back in, and you will automatically have a fresh version of the tutorial notebooks directory with the most up-to-date versions of the notebooks, and that directory will be read-only, which means that you can open a notebook and you can execute it, but you cannot save your changes to that directory. And it also means that any future time when we update our notebooks, which is a pretty regular occurrence, you will always automatically have the newest ones with no conflicts. So if you're not a Git user and you've experienced these conflicts that happened in the past, highly recommended. The other change here, so if you don't change your directory to read-only and you want to keep it writable, when changes are detected in that directory, you will see a warning file appear. It's called 00 warning readme. And that's to alert users that you might have old versions of the notebooks there. So hopefully these changes will just help everybody keep on track of new versions of the notebooks. So we've got a good schedule of delegate assemblies coming up in the future. Right now we're September 30th, so we're doing data visualization today. Next week at this time will be Stat Club. Our next delegate assembly will be Friday, October 14th, and you can see the upcoming schedule here. We're now moving into our delegate presentations part of DP0.2. So we're ending sort of the formal tutorials that the community engagement team does, and now we're inviting people to come and give presentations. So if you want to volunteer to present in early 2023, just reach out and let us know. We'll set it up for you. You can present on your DP0 related work. If you don't want to do a full like 10 to 50 minute presentation, but you do want to give a little flash talk on something that you've tried with DP0, a plot that you've made, just your science interests, whatever. On Friday, December 9th, we're having the delegate assembly for that day be like a little bit of a year in review, just to summarize like what we've done so far in DP0 this year. And then the main focus though is going to be delegate flash talks. So 1 or 2 slides for anyone who wants to present, and we'll all get together that day and sort of just share, you know, what we've been doing with DP0. So more information will be sent about that in the future. So coming back to notebooks and versions, today Leanne's going to be presenting notebooks 06A and 06B. If you have the most up-to-date version of that notebook, you will see that it was last verified to run yesterday. And in the header, it will also say that it works with LSSD Science Pipelines version weekly 40, which is what we just updated to yesterday. So do a little check on that. And I'm going to post the link to these slides in the chat, because if you don't have the most recent version, there are a couple of fast fixes here to make sure you get the most recent version for today's tutorial. So that said, I'm going to hand it over to Leanne now. She's going to take you through notebooks 06 A and B on data visualization. And then as per usual, once that's done, we'll come back and we'll set up some breakout rooms and we'll have some fun. And as always, if you have questions, we are watching the chat continuously. So if you didn't catch anything that I just said, you know, the slides are coming in the chat and feel free to ask questions at any time. Leanne, are you ready?
Yes, I am. Thank you, Melissa. I'll just share my screen. It's that one. Okay, does everyone see my screen?
Yes.
Correct screen? You can see my mouse moving around?
Yes, I can.
Excellent. Okay, just let me just move a few things around. Zoom always reorganizes your windows when you share screen. So it's just nice to be able to see. Okay, right. Thank you. Good morning, everyone, and thank you for joining today. Today's tutorial, we're going to look at two tutorials today, as Melissa said, 06A and 06B. But the theme of both of these is interactive visualization, how to go beyond just making static matplotlib plots and how to really get down and dirty with your data, how to use visualization to gain insight from data. That's the key message I think I want to get across to you today. Melissa?
Yeah, there's a request to remove the directory structure from the left. I think you do it with Command B.
How do I do that?
I think it's Command B or
Command B?
Or you can that works. You can also just click on the little folder icon in the upper left.
The folder do it as well. Okay, thank you. Is that better for everyone?
I'm going to assume that it is. Yeah.
Noted heads. Okay, thanks for the notes.
Might need to increase the font size a bit, because the comment was actually, could we make the code bigger?
How's that looking? I can probably also remove that. We won't need it. How's that looking?
That looks very visible to me.
Okay, great, because I'm on full screen here on my big screen. Okay, great. So, okay, so as you see, I have two tabs open. There's A and B. We're going to start with A. A is interactive image visualization, and B is interactive catalog visualization. And just before we start, the key message I think I want to get across to you today is that the purpose of visualization is insight into data. It's not to make pretty pictures. It's not just to generate plots and have thousands of plots and say, oh, well, here's some plots. What do I do with these? I'll go and have a look at them and what can I learn? It's about gaining insight into your data. And you probably all work with Matplotlib and other tools that we've used for a long time. And these tools are great for getting started, initial basic plotting of data and learning something from your data. But there's a whole new suite of tools that have been developed recently, probably over the last 10 years or so, referred to as PyVis or HoloVis. It's the PyVis ecosystem, the HoloVis suite of tools that enable really powerful interactive image visualizations. And they allow you to, they just provide a much easier way to do multi-dimensional analysis on the fly interactively. And so that's what we're going to take a look at today, how to use these tools and how to use them to gain insight into your data. So in this interactive image visualization, we're going to work with a CalEx and a COAD image, and we're going to work with the source and object tables to have a look at how we can interactively explore these data products. So this is the usual introduction here. I won't go through this. I think we've been through this in previous tutorials. We run a set of package imports as usual in the beginning. It's useful just to inspect the versions that we're using. Here we're using the tools Bokeh and HoloViews, and we import these. You can see that these are imported here in these imports. This is what's new as opposed in addition to the usual set of packages that we import. We'll just set some warnings to ignore some warnings. And this cell here is what's important. HV is HoloViews. We import HoloViews as HV, and we set the extension to be Bokeh as the backend. Now, HoloViews itself is not a plotting package. It provides a set of tools that It provides a set of tools that allow you provide a very simple way to produce interactive plots across a variety of data types. And it works with a number of plotting library backends. Bokeh is one of them, which allows interactive plots, and Matplotlib is also another one of them. And one of the exercises to the user I put at the end of this is to swap out this extension here and put Matplotlib in instead, and set Matplotlib as the backend, and see if you can do similar things using Matplotlib rather than Bokeh. Okay, an output notebook just sets the output of the plots, the images we're going to see to come up in the notebook. We're also just going to run a simple function here, which converts a Butler data ID into just a simple string that I can use as a nice header for some plots. So the first step in any visualization is to prepare your data. It's very important to prepare your data in a way that makes it easy to plot it, so you can learn from your data. So that's what we'll do here in section 2. We'll configure a Butler. I won't go through the details of this because we've had some Butler tutorials in the past. So we set up the Butler. It points to the DP0.2 Butler repository. Now we're going to retrieve a calibrated exposure and the sources of the source detections within it. So we define our calibrated exposure ID. We use butler.get. We make sure that we've got it, format the string, and we just print out some information out of it. So it's visit 192350, detector 175, and the band is I. We can ignore this warning here. This will be removed in the near future. So that's the calibrated exposure. Now what we want to do is query the source table in the Butler for this data ID to get the sources that were detected on this single exposure. So we run that, and we see that we get, there were 2,548 sources detected in this calibrated exposure. Now we're going to retrieve a deep coad, another image. This is the data ID, so it's track 4226, patch 17, and band R this time. We use butler.get for the deep coad. We assert that it's not none. You can uncomment this here if you want to get some information about the coad itself, the input. One of the most interesting things about coads is this one here, which allows you to get the lists of the visits that contributed to making the coad. We won't go into that in this tutorial. Now what we're going to do, in a similar way as we did for the calibrated exposure, we've got a list of the sources that were detected by the LSST science pipelines on it. We're now going to get a list of the objects detected in the coadded exposure. And you can see this is a much bigger number. It's close to 40,000. This is because it's a coad, goes much deeper. So you see many more fainter sources, objects. And so we expect that we would have a lot more detections in this coad. Now, just before we start doing some interactive visualization, we're going to do a little bit of exploratory analysis. Well, not really analysis, but visualization on this data. And we're just going to use Matplotlib here, which is, it's a good tool for just doing some initial basic exploration of the data. Here we just do some data wrangling, and we use Matplotlib to plot the data. And so here you can see, here is a plot, a distribution of right ascension and declination of the sources detected in the calibrated exposure. And here you can see the objects detected in the coad. And you can see these are two completely different objects. There's no relationship between this CalExp and the coad. We've just taken two separate images here. And here you see a distribution of the apparent magnitude in each of them. And you can see that for the coad objects, clearly this goes much fainter than the CalExp. So this is what we expect to see. Okay, so now how do we go beyond just simple visualization? HoloViews is one of the tools I want to introduce to you today. It supports easy analysis and visualization by annotating the data rather than utilizing direct calls to plotting packages. It provides a level on top that makes it just easier for you to plot multidimensional data. As I've just said, HoloViews supports several plotting libraries, and at the end of this exercise, if you like, you can go and try to use a different backend than Bokeh. The basic core primitives of HoloViews are called elements, hv.elements. These are simple wrappers around the data that provide semantically meaningful visualizations. So an element can be a set of points, it can be an image, it can be a curve, a histogram, or a scatter for a scatter plot. And you can go to the reference gallery here for HoloViews to see the various different types of elements that can be created. So how do we use this to visualize our calibrated exposure with HoloViews? In this first example, we're going to take the CalExp and visualize it. We're going to use the image element in HoloViews to visualize the calibrated exposure. Before we do that, however, we're going to make use of the AstroPy visualization library to define a stretch and a scale interval and apply that to the calibrated exposure first. So this is what we do here. We define a transform, and then we apply that to the scale to the image. And we apply that to the data. So we have to extract from the from the Calix object itself, we extract the image and the array of data to scale that. Now, because LSST's image classes use a pixel indexing convention that is different from that used by the NumPy and the array objects and the convention used in FITS, we have to flip the data array. So we do that, and then we define a set of bounds on this flipped image. You can find further I don't have time to go into the details of this here, but you can find further information about that in this link. One of the things about HoloViews and as well with Bokeh is that it separates the data content from the presentation of the data. And the presentation of the data is defined through a set of options. And here we define these as a dictionary. So we just define the height, the width, where we want to put the x-axis, padding, font size, all sorts of things like that. And we can define these very simply here. And then we create the image element with simply a call to image. hview.image, we pass our scaled image, we define the bounds, we define the dimensions that we want, X and Y, and then we apply the options in this dictionary by typing .opts, and then we add a whole bunch of other ones, and then a reference to the image ops. So we define image ops here as a set of fairly standard ones we might want to use across many different visualizations. We put a reference to those here, but you can also in this opts call add a number of other ones as well. Like for this specific plot, I want the label to be X and Y, and I want this to be the title of the plot. And so if we run that, and then we display the image, that defines the image, and then we display the image. And so now we see this is the image, the calibrated exposure that we've retrieved. And if you hover over this, you'll see that everywhere you go, it gives you, this hover tool gives you the point, the location, the X, Y, and the Z coordinates, the Z being the intensity. And this is defined here with this tool called hover as part of the ops. We elected as part of the options to put the hover tool in. And this hover tool then comes up here in the toolbar to the right. This is the hover tool. So if I turn the hover tool off, you'll see it's not there. If I turn the hover tool on, it will give me information about any point. This is just very simple annotated information on the plot that you can use. This allows you here to save it to disk. This is the wheel zoom, so I can use the wheel on my mouse to zoom in and out. I can also use a select zoom like that. This is a reset, and this pan tool allows me to move it around. So these are just some very simple tools that allow you to play around with the image. Okay, so now what we want to do with our Calix is we want to say, well, this is very nice. This is the image, but what did the LSST science pipelines detect? Did it detect all of these objects that we see here? So we want to overlay the source detections on the calibrated exposure. So we will use the points element, the HoloViews element called points, in order to overlay detections at points on the image. We get the coordinates for our calibrated sources. So Calix sources, as you remember, this was the query to the source table. So we want the X and the Y points. Before we do that, however, we're going to create a custom hover tool. The hover tool that I showed you is just the default. This is now the custom hover tool, so you can specify formatting, you can specify formatters. Here I just use printf, but you could, for example, format as a date time, you could format as a numeral. There are many different formatters that you can use. And here I specify the number of decimal places that I want in this. And so then I create a detections element called hview.points. I pass the coordinates that I defined here before, X and Y. And in the options, I just set a few things like the size, the fill color, and then for the tools, I pass here my custom hover tool. So I define the custom hover tool as detections hover tool, and now I'm passing that there. So you run that. Now, to overlay sources on top of an image, you use the multiplication of the star operator to overlay one element in HoloViews on top of the other. So here we have the image with the options. I'm going to remove the tools from the image because otherwise there'll be too many tools and it will just be crowded. And then I overlay it with this multiplication with the detections, and I specify that I want the detections hover tool. So now you see the same image as before, and if I hover over it, I get the location of the detected source, not of the point in the image. And then you see also the same toolbar here as before. Are there any questions? Just pause for a second. Doesn't look like it. Okay, so that's very nice if you want to just explore and go around, have a look at the images. You can also now do interactive image exploration with streams and a dynamic map. This allows us to wrap callable objects, the concept behind this is that things can change over time and you want to automatically refresh and update things as they change over time. So we're going to look at creating a dynamic map here and a stream, which we can overlay on top of an image. So we define a dynamic map with a box stream. This defines a box that we can draw on the image so that we can explore selected regions of the image, not just the whole image. So we define a set of bounds and we create a stream, which is bounded by these bounds here. This is just the default starting point. Our source is the image that we have above, and this defines a bounding box. And for the dynamic map, we apply this stream, which we've called box. So we apply this stream to define the dynamic map that we overlay. It's a bit easier to explain if I show it to you. So now if I plot the image again, I'm going to put the tools hover and box select back, and I'm going to overlay this dynamic map. So I haven't put the source detections on here this time. I've changed the tools. So now you can see there's a box select tool. If you hover over it, it says box select, and the hover tool's there. All right. And now if I select box select and I choose a region that defines a box. So this is what the stream did before. It allows me to define a box on the image. And then if I type box, this tells me what the box is in terms of the bounds. So it tells me exactly the dimensions of that box. So this, if you come back here we defined an initial box, which was just set to 0, 0, 0. I draw a box on my image that then sets the coordinates for the box. That's linked as part because we have a dynamic map on top of the stream. And then when I call box, it gives me this box. And so this is useful because if I'm looking at an image and I say, well, gee, that looks a bit strange. I actually want to drill down here. I can draw the box. I can get the coordinates and then I can pass. I could, rather than just display this in a notebook, I could take this box and I could pass it straight into an analysis routine, which would then say compute some statistics or do some additional drill down into the sources that are in that box.
Leanne?
Yes.
Is this the one where most delegates won't have the box select?
No, it's not. This one should, the box should be here. We maybe just check that box should be there. Is that correct for everyone?
I think.
Actually, I didn't see it when
Okay.
I
If
uploaded the new one.
not, as an exercise to the user, you go to cell 23 and you just type that in. And then the box will come up.
Yeah, I think for me, I had to add the .ops.
Did you have to add .ops? Okay.
Yeah.
Okay. So we can also look at that, playing around with that after the tutorial as well. So yeah, you have to actually add this in. The box select is not part of the default set of tools. So we have to add in tools, which includes the box select. You get all the default tools as well, like the pan and the reset.
Yeah.
Okay.
Cool.
So that's great. So that's how we do a box select. If you want to define a region, you could also define a lasso. You could define all sorts of different shapes as well. So that's a box. We can also use a tap stream instead of a box select. Now, tap stream allows you to tap a position on the plot and then get the coordinates for that position. So here we use hv.streams tap. Our source is the image again. We define a position. We define the marker. And then we overlay the marker. So the dynamic map is, we call a marker. So this dynamic map now takes the pos XY stream, not the box stream as before. And you can see here's the X. We defined initially the X to be 0.5, 0.5. I can move that X to anywhere. I can say, gee, I want to take a look at this. Let's put an X here. You can't see it because it's white. X marks the spot. And then I can print out the value at that position. And I can print out anything I want. So you get the position. I can move it again, and you'll see that now it comes up with a different position. So if I want to sort of, go around the image and say, well, gee, that looks interesting. Where's that? And I can extract then that position. And this here, rather than just printing to a screen, could actually go into a function that then does some more complex analysis and brings up more information. Yes, you're right, Melissa. That was the right one. The one I was thinking of. Sorry, I forgot. We are now at the end of the tutorial. Okay, so that's just an introduction to how you do interactive image visualization using the sources detected and a calibrated exposure and some coads. So I've got some optional exercises here for the learner. If people want to try these in the hour after this, or if people want to try them in their own time, please go ahead. One of them is to try a different backend. Matplotlib is one of them that I think people know and love. In section 3.1, you can try using a co-added image instead of the calibrated exposure image and use the object detections. In section 3.2, you could try extracting additional information about the sources and adding it to the custom hover tool. So rather than just having the XY position plus the intensity, did you just lose my screen? Okay, hang on, it's my screen connection. It's okay, it's back. You could try adding a different information, like, for example, corresponding, you could get the RAN deck, or you could get the PSF flux, for example. You could add that to your hover tool. And then in section 4, you could try using a different stream function to interact with the images. Okay, so that's the end of the introduction to interactive image visualization. I just pause there and see if there's any questions around that before we move on to catalog visualization. Okay, sounds good. Okay, so let's move on to catalog visualization. In this one, we're going to use the same libraries again to explore some of the catalogs, the source catalogs, the object catalogs, and to explore those data sets. Another tool that we're going to introduce here on top of HoloViews and Bokeh is Datashader. Datashader is used to accurately render very large data sets quickly and flexibly. So as we get to the LSST catalogs are going to have billions of entries in them, and trying to plot billions of entries by setting the alpha parameter to be 0.1 is going to end up being a bit of a disaster and a nightmare. So that's not really a scalable way of exploring the LSST dataset, and we need a better way of visualizing very large data sets. And Datashader, together with HoloViews and Bokeh, provides one such solution. So usual gamut of package imports, except in this time we're importing Datashader as DSH. So HoloViews is HV, Bokeh is Bokeh, lots of AstroPy, science platform, and then we have Datashader, which is DSH. Always good to check the versions of what you're running. We'll just ignore some warnings again. And we will set, as before, the HoloViews backend extension to be Bokeh. Okay, so I just ran those again. Now, I'm not going to run these ones here. I've pre-run this section here. We're going to use the TAP service to obtain a set of data from a table. I have pre-run this because it's a big query, and if everyone runs it at the same time, it will take forever. So what I do is I just set up a TAP service instance. I define a position on the sky. So I use the AstroPy sky coordinates object. I just define a position on the sky, and I set a 1 degree search radius. The query we were going to pass to the TAP service is a cone search about this point that will cover 1 degree. And we're going to extract a select set of attributes of each of the objects, so the coordinates, the object ID, the extendedness, the magnitudes, the G, R, and I magnitudes. And then we're going to also do some simple filters. We're going to use detect as primary. We're going to set a magnitude cut of 27. And as we're going to use the extendedness parameter in this demonstration, we'll make sure that the extendedness is not null. So that's we print the query. Because this will return a very large data set of 1.3 million objects, we run this as an asynchronous query. This has been covered in another tutorial. I think it's the introduction to TAP or the introduction to ADQL. It can take a few minutes. So I pre-run this. So I submit the job, I run the job, I wait till it's complete. It took 25 seconds, and I get back a data set of 1.3 million objects. So now the first thing we're going to do is compute some additional data. So we're going to use we're going to compute 3 colors from the apparent magnitude. And then we're going to use the R-band extendedness to classify objects having a shape type. So we're going to call it pointer extended. So we map This is 0 for a point and 1 for extended in the database. So we're going to map that in our data set to a name because that's easier to work with. And then we're just going to assert that our data set is what we expect. Okay, so now let's have a look at this data. We've done a little bit of pre-preparation around the data. 1.3 million is a very big data set. If I try to show you everything you can do with hollow views with that, it'll take a long time to render. So I'm going to create instead a 2% random subsample of this data set just to demonstrate some of the basic functionality. So this just does a data sample, 2%, and I expect to get something of the order of 20K. So almost 27,000 points now. So this is just a smaller data set to work with. We will, at the end of this tutorial, plot the whole 1.3 million data set. Don't worry. All right, so let's do some simple plots, some very simple plots. The whole idea of hollow views is to provide a very simple and easy way to visualize data, catalog or image data without worrying about the details of a plotting package. So as I've already said, the hollow views use elements. These are wrappers around the data to provide meaningful representation. So what we're going to do with this data we've just extracted from the catalog is make a very simple scatter plot. If I just remove this here, the way to make a simple scatter plot is just hv.scatter and you pass your data set. That's it. I'm going to add some options, as we've seen it already, just to remove the toolbar, just to have a clean plot. And that's it. That's how you make a plot. It's very simple. You don't have to worry about any of the details of the layout or the set out or the subplots or the layout. It's just a nice way to start looking at your data. There's no hover tool. There's no interactive visualization. That's just a very simple plot. You can play around with the options if you like. Now, the 20K data set, as we saw before, contains many columns. It's got columns for the magnitudes, then we added some color columns. It's got columns for extendedness. How does it know what to plot here? If you pass it a data set and you don't tell it which columns to plot, it just by default takes the first two and scatter does a two-dimensional plot. So it's just right ascension versus declination. Declination versus right ascension. Now let's do a little bit more. Let's now make a histogram of this data so we can bin the data. We will first bin the data using NumPy. I think most of you will have run this before. Now we specify exactly which column we want to bin. This is going to the numpy.histogram. You can select a method. We say we want to bin the right ascension column, and this provides us with the bins for right ascension and the counts. And so to create a histogram with hollow views, we just use hv.histogram, and we pass the bins and the counts for the bins, and that's it. Okay, that's simple. You don't, everything that's in .ops after the ops, you don't need this to plot the data. So one of the things I really like is it separates the content of your plot from how you present the plot. And so if you don't have anything after ops, it just gives you a default plot that looks like that. That's it. So, but we're going to add some options. We're going to give it a title. We're going to give it a color. We're going to define a width and a font scale. So we define it there. We call it RA distribution because we're going to reuse this later on. And then we just plot RA. And so now you get a histogram. You see the toolbar again at the side. You see the zoom tool. So I can zoom in. I can reset. I can save it to disk. I can use the wheel zoom to move around as before. Same as for the image that we just looked at before. So there's a simple histogram. It's just hv.histogram bins and counts. So this isn't too useful on its own. So let's see what else we can do. Now we want to create a layout of unlinked plots. A layout of unlinked plots is just when you have a series of plots sitting next to each other or on top of each other in some sort of grid, but the data sets within them aren't linked. And we do this by creating what's called a layout. This is a type of a container that contains any type of hollow views object. So a layout can contain an image, a scatter, a histogram, any type of object. And we can put these next to each other. There are many different types of layouts. You can have a look at the reference gallery here, and you can see more details on how to build composite objects. So the way we put things side to side is now to use the plus operator. So the first thing we're going to do is recreate that scatter plot that we had above. We're going to just add a few more things to it. So here we're going to specify. We take the 20K data set. We're going to specify the X and Y axis that we want. Then we're going to add some options like just the toolbar, the width, the size, etc. A few presentation options. And then next to it, using the plus operator, we'll plot the RA distribution that we created just here. And now we'll change it to be height and width of 350, just because we can. So we define that. And so now this composite is called sky plots, and we plot sky plots. And so that's how you lay them out next to each other. And so there's one common toolbar here that applies to both. So for the sky plot, we defined a hover tool, and you can see the right ascension and declination coordinates. I can zoom, but you see this is not a linked plot. So I'm not linking that to that, which means when I zoom here, it doesn't zoom here. I can, however, zoom here, but that's a very different zoom to that. And then the reset resets them both. So this is really just a layout option. And you can try playing around with those. But what's really interesting to do now is to try to link the data sets in here. So that if you manipulate one plot, then you also see the effect in another plot. So before we do that, though, we're going to define some default plot options, because typing the same plot options all the time is tedious. I'm going to call this plot style bokeh, and then this one here is plot style matplotlib. I'm not going to do any matplotlib myself, but this is to show you that for things like plot styles, you have to create different dictionaries of objects for different backend libraries because they have different parameters. So, for example, bokeh, matplotlib takes C as a color, but bokeh won't understand C as a color. So you can't just use them interchangeably. Marker S is also matplotlib, but if you put marker S here, it won't mean anything to bokeh. So typically your customizations, plot customizations like this do have to be tool specific. So for this one, I'm going to set plot style as the plot style bokeh. If you do go back and try matplotlib, just change that, and then you can run the whole tutorial again. So now let's create a scatter. This time we're not going to subset the data 22K. We're going to tell HoloViews which axes we want to plot using K dimensions and V dimensions, the independent and dependent variables. So here we want to plot the GMI versus the C model magnitude. And in our options, we want to invert the axis. We want to have, here's some labels. And then we want to just point to and include our generic plot style options that we defined above. So this now shows me a scatter plot. I didn't turn the hover tool on here, but you could turn the hover tool on as well if you want. Yeah. So the thing. One thing to note about these dimensions here, the independent and the dependent dimensions here, is that they've been specified as strings, but they're in fact rich objects. So you can specify RMI and GMR as a dimension with a label that's useful for programming, and then a label that's useful for displaying, and you can also set the range. And so now we can replot that above. Sure, here. Now I can pass to scatter points, and I can just specify K dimensions and V dimensions as GMR and RMI, and then that encodes the label and the range that you want for the plot style. So we're going to use this now and use the histogram method to show the distribution of samples along both dimensions. This is a very useful plot that I'm sure many of you have used. This is a scatter plot. We haven't shown this yet, but we're going to add a histogram to the scatter plot, and we're going to add it in both dimensions, in both the GMI and the GMR dimension. So we run that, and then we plot it. And so this now shows us, here's our R minus I, G minus R plot, and then we have a histogram on either side of each of these. And so as you move it around, the histograms will move with it. If you choose the box select tool, the zoom tool, as you zoom in, you can see that the histograms are dynamically recomputed as you zoom around the plot. Okay, I'll just pause there. Are there any questions on that? Are people following along? Have you been able to follow along? I'm getting a thumbs up. Is that a question from Jeff?
Yeah, just a quick question. The histograms attached to the axes, that's just that method, the .hist method?
That's it.
And it knows to do everything else?
Yep.
So if you just gave it one dimension, it would just plot the, like the histogram on the x-axis, for example?
Yes, but I obviously have to, or it should, but it might have to go through and It should.
Anyway, that's super nice.
It should, in fact, 'cause I originally had it as one and then put both in. I might have to run all of those again. There. I've probably reused something that I've overwritten, which I'll go back and check later. But yes, if you just provide one dimension, it does it in the RMI side. So here's R minus I, and so it histograms in R minus I over here, but it doesn't histogram in G minus R.
Nice, thanks.
Now I've got to run it again. I think I'm not sure why. Maybe I reused or something, but I'll work that. I'll try and work that out later. But yes, if you just provide one or the other, it will just do one or the other. So that's a very nice addition to a scatter plot. So it's very, very easy way. You just tell it the dimension, the bins, and adjoin just means you adjoin it to, I think if you are this, I'm not sure where, I forget where this puts it. Okay, I have to probably rerun. I'm not sure. I have to rerun that. I'll have to check that. Ah, okay. So then it doesn't adjoin them. It just creates two new histograms. That's all. So rather than adjoining it to your scatter plot, it creates histograms from the scatter plot, doesn't adjoin them, but just presents them as separate histograms.
I think it's because you define call underscore call in 52 there. And then
Yeah, you're right. Yeah. It's reuse of variables, which is very bad programming practice, and I will clean this up afterwards. Okay, so yeah, and these plots, as many of you know, are extremely useful for understanding your data. Okay,
there's just a comment in the chat that you can save your plots in HTML and then put them straight into a web page.
Yes, you can.
Yeah. Is
Yes.
that the little disk symbol? Is that how you save stuff?
What format does that? No, that dumps a PNG.
Mm.
But yes, you can do that. I haven't got an example of how to do that here. If people are interested, I can provide an example to do that.
Cool. Yeah.
Yeah. There are there's maybe a couple of extra dependencies you have to add in order to do that. But yes, you can. I mean, a lot of the use for these interactive plotting tools is to display things in web pages, so people go to a web page and they can see what's happening in real time, for example. I mean, something like this might be very nice to show how the survey is progressing over the 10-year survey. Okay, I'm going to put a little thing in here on magics because people use them. I don't. But just to say that magics, these are a technique to apply customizations in cells. They are only used in notebooks. It doesn't work in standard Python code. HoloView supports magic commands. They're a much older approach. It's not standard Python. And all those opts that we've been setting in .opts, you can set here in, this is the magics command opts for scatter, and then you set all these opts here, and then you do hv.scatter. You can still set additional opts with .opts. And they all get taken into account. And you can see the hover tool. So I added in a hover tool. I didn't specify what I wanted, and you can see that it for every point, it gives you everything that's in the data set. So we'll see how to customize a hover tool in a minute. All right. In fact, we'll see how to customize a hover tool right now. So as you can see, this is just unreadable, right? So again, as we did for the image notebook, we create a custom hover tool. I'm going to call it RA-Dec hover, because here in my tooltips, I define that I want RA-Dec, and then I want the R magnitude, and then I want the shape type. And the format is here. I can say I want printf for this, then I want a numeral for magnitude, and a printf for the type. And you don't need to put this in here. This is the default, just to show you that you can set a point policy as well, which in this case is to follow the mouse. So the tool changes as the mouse moves. So now we can do our scatter plot again of 20K points. For options, we specify the tools to be our custom tool, and then we apply our standard bokeh plot style. And so now you can see we just get RA-Dec on one line, RMag, and the type. So it's very easy to customize what you want to see in your hover tool. So you can zoom in And that just gives you for 1 point. So if there's 2 in the field, see here, it can't distinguish, there's too many points, so it gives you everything that falls under the cursor. Okay, now we're going to take a look at Bokeh now. This is the backend plotting library we've been working at. You can, of course, work directly with Bokeh. You don't have to go through a tool like HoloViews. You can make plots just directly with Bokeh. And Bokeh is also very useful to add connected interactivity between plots and show how different attributes of the same data can be viewed. And this is what we call linking. You link plots and you select a point in one distribution and you can see it in another distribution. So there's a link here to some more tutorials from Bokeh itself on linked brushing. Right, so the first thing we're going to do is a bit of preparation of the underlying data, and we're going to use a column data source object to make our data. So here we create simply a dictionary of data, and we're going to define what the columns are and what the data we want to go into it is. So we're going to define x0 as the right ascension subtracting the center point. So remember, we did a search about a point. We did a cone search of 1 degree about a point. So we're going to define x0 and y0 to be every point in the data set subtracting the center point. So we get an offset from the center point. We're going to add in the G minus I color. We're going to add in the C model magnitude, the C model G magnitude, and then we're going to add in the right ascension and declination coordinates themselves for each of the points, and use that to create a column data source object. Now, once you've created this, you can, of course, add more. So we're going to add a few more onto this. You just do source.data, and you define a new column. So we want to add in also the object ID. We want to add in the R minus I color, G minus R color, the RC model magnitude, the shape type, and the extendedness. Oops, sorry, I didn't run that one. Run that one, and run that one. Now we're going to create a points view on the shape type. So this is used primarily to filter data. So let's say I want to provide a view of this data set around the shape type. That's this one here. So I make a column data source view object. The input data is this source that we created before, and our filter is a group filter, and we're going to filter on shape type and select point. So this is a way to provide a point filter or a point view on the data. And we can apply this as we do plots to very simply look at different data within this large set. So we're going to create linked plots now for data brushing, and we want a custom hover tool for each panel. And so this here just creates a hover tool with different tooltips for each panel, because I'm going to have different data in each panel, so I want to display different information. On the left, I'll have the right ascension, declination coordinates, and the shape type. And on the right, I'll have the object ID with information about the color and extendedness. I define a set of tools that I want, and then I create my tool object. This here shows how we create a figure with Bokeh. So we use figure. From Bokeh, we've imported figure. We define the tools. So this is the left-hand plot here. I'm calling left. So our tools are our left tools. Then we define a few more customizations. And then we have the X and the Y. The points we want on our figure, we want them as circles, and we want them to be the X0 and the Y0. So these are the center, the centered positions. We define a few more colors, and you can see here with Bokeh, this isn't like HoloViews where you have the data and then the options, the customizations separate. You can see this is sort of all part of the same call. Then we just define some ranges, some axis labels. This is for the left side plot, and then we do the same for the right side plot. Set the tools, set the data. We also want the shapes to be circles, set a few more customizations. Oh, what's happened there? Ah, I forgot to run this one. Sorry. Okay, I forgot to run points. Now I'll run that. Now I'll run this. Right. So now I've defined my figures, and now to plot two Bokeh plots, I have to use grid plot. This comes from Bokeh left and right. So I define P and then I show P. And you see this is sort of much more familiar syntax that you're probably used to with Matplotlib in terms of setting up grid plots and aligning things side by side. So now we have two plots side by side, but these plots are linked. So if I hover here, this, Melissa, is something else I found yesterday, sorry. Let me fix this. Okay, so now I just hover here. You can see that the cursor has fallen over two objects. So you see the two different object IDs. You see the right ascension declination and the type, which is what we specified as being part of our hover tool. But if you look to the right, you can also see in red, I can't move my cursor, but you can see two dots in the red. And these are the exact same points in the color magnitude diagram. So this way you can link spatial data in a spatial distribution to data in a color magnitude diagram. If I use the box select here, we'll highlight the data. So if I want to, let's just go reset, I want to say, you know, is there any spatial correlation between this group of points here? No, doesn't look like it. At least not in this 1 degree search area. I wouldn't expect there to be. But this is just an example of how you can select regions in one area that might be outliers or extreme events or something that looks a bit odd and say, well, gee, I wonder what that looks like in a different space, in a sky plot or in a spatial distribution or in a color diagram. And if you link these plots together, you can do very easy interactive exploration of data sets like this. Okay. So that's all very interesting if you're playing around, but what you really want to do is say, well, let's say, oh, we've got a set of points up here. Let's just have a look at these. And now I want to do some further analysis on this set of points here. What you want to do now is have linked streams, not just linked plots where you can see one set of points in both, but you want to link the streams. Which will come to the top of the hour. I need to go a bit faster. So now we want to do calculations. We saw streams before with the interactive image visualization. The same as before, we define a set of points here, and then we set up a stream, which is just a one-dimensional selection stream we're going to set up here. Then here we define a function which will do some calculation on the data that is streamed from the plot via my selection. It gets streamed and into this function. And I'm just going to calculate a mean. So if there's no selection, I do nothing. And if there is a selection of data, I calculate a mean. Now we have to, in order to combine this, we have to use a dynamic map as before. So this stream with the function that goes with it, we define as a dynamic map. And then we put this side by side with our points plot, which is just our scatter plot. And so I removed the hover tool. So there's no hover tool. Sorry, I removed the I moved the hover. So here is just the XY, the right ascension declination, your spatial distribution of these points. There is no selection at the moment. Therefore, you see no selection written up here. This is part of this function. So now I'm going to do a selection. The data that I select in this box is then passed via the stream into the selected info function, and it computes a mean. And it tells you the value and it shows you the data set. So then this again, let's say you plot a color magnitude diagram or you plot any sort of diagram, you say, oh, boy, there's a weird bunch of points out there. I'm going to select those, and then you can automatically compute a whole bunch of additional functionality on them. And then that you can do interactively, but then you can also call that and you can get the selection indices here. I've just printed the length, but you can actually get the indices, and then you could take that indices and you could pass them straight into a whole other analysis routine that you might send off as a batch job somewhere to do very detailed analysis, and then would come back and give you some results. So this way you can combine interactive exploration with some very powerful backend processing. All right, the reason I put length there is because that's long. Put that back. Okay, we're going to move on to the last part now, which is Datashader. I'll just pause. I don't have very long, but are there any questions on those ones just before I move on? All right, now Datashader, which you've all been waiting for. Now we're going to look at how to plot millions of points. Melissa, can I go over 10 or should I try to shorten this?
I think just go over. I took some of your time with my long announcements.
Okay.
Yeah, so just keep going.
Okay, I don't think I'll be any more than 10 minutes.
If people have to drop off, they have to drop off.
Okay.
But keep going.
Okay, so these interactive features work very well with data sets of up to a few thousand points, but to efficiently explore larger data sets, we need to use a different model for exploring data. And this is what Datashader is for. So now we look at plotting thousands of points. Let's just first plot a color diagram using Bokeh with a customized tool. This is what we did before, and we're just going to plot this here. An example. Okay. Now, what we see here is that even with a medium-sized data set of 20K points, you can see that this plot suffers from overplotting. Okay, this is very clear already. And even in here, if you look at, what have I set? I've even already set an alpha of 0.2, and I've set a circle size of 2, and I still suffer from overplotting. And we've plotted both the point and extended sources, but you really can't distinguish them very well at all. So this plot's a bit useless, to be honest. You can, now let's try to zoom in on it. But as we zoom in, you can see that the fact that we have an alpha makes everything very faint, and it doesn't really sort of help us very much either. It sort of washes out the detail in the sparser regions. Okay. An additional problem with this is that you can't add too many glyphs to any one plot, otherwise you just get a plot that's too big and you can't render it. And I'm sure you've all suffered from that problem before. You've tried to plot a data set of 100,000 points and your plotting program has crashed. So we use, in order to get around this, we use HoloViews together with Datashader to plot billions of points. So to demonstrate this, we're first going to start by creating a HoloViews object called points that will hold the data. And then we're going to create a link stream, as we have before, the dynamic map. And then we're going to apply the Datashader, that's here, and just set some options. And now we will render this. Okay, so now you see the same plot. I think it's the same plot. Yeah, the same plot now using Datashader, where the data has been binned, it has been aggregated. And as you zoom in, you move this around, as you zoom in, the data automatically gets re-shaded, re-data-shaded, re-binned, according to the density of data you have on the screen, according to what's appropriate for the level of zoom. So as you change around, the shades of the data point change according to the local density. Okay. Right, but this, I mean, if you look at this though, it's there it is. It's really too small though to data shade. This is only 20,000 points, and then it doesn't really show the full power of it. What we're going to do now is use this technique to plot the full data set, the millions of data points that we achieved, that we selected before in our initial query. So we create an element using points, HV HoloViews points, and the data we want is G minus R, R minus I. Then again, we create a linked stream, and we apply the Datashader to this whole plot. So there, in 600 microseconds, I have rendered 1.3 million points using Datashader and HoloViews. And now you can see, look at this, look at the detail now that you can see in this color diagram, as opposed to the complete lack of detail in this one. And this was only 20K points. Now we can see structure in here. We can think, well, now, wow, gee, you can think, what's this here? What's this very, very strange thing here? Let's use the wheel zoom, move around. What's all this here? That's weird. And so now you can see that structure that you couldn't see before. So this is really very powerful to use with Datashader. Now, now we want to add a callback function. A callback function, like we did before, it'll allow us to retrieve a set of indices of selected points. So if we want to say explore these strange features here in the plot, we can use a box selection tool to select those points like we did before in the previous plots, and then do some additional analysis. So before we move on, we need to select some data. I'm going to select this region here. So there's the box, and we can do that because we set up the linked stream before when we made this plot. So remember, this is a plot, a data shaded plot of the points overlaid with a dynamic map, which includes a stream with a box defined to take data from this box and stream it into some function that will do additional analysis. Oops, didn't mean to do that. And so now this tells me that the box selection contains 145,000 points. This is the selection defined here. And I can now take those points and I can go and do some analysis with them. So now I think this is, okay, this is the very last part. We do now an interactive selection. So now what we're going to do as the final example is plot a spatial distribution on the sky of all the data, the 1.3 million. We're going to use Datashader, obviously, and then we're going to link it to a two-dimensional histogram of that same data, and then use a box selection in the spatial distribution to change which data get binned. So we just define our data set here as this is the full data set now, not the 20K, and we define our dependent and independent dimensions. We create a points HoloViews object. We define the bounds. We set up a box stream so that we can select the data via a box, and then we create a dynamic map, which is defined by that box stream. Then we want to define a custom callback function. And this callback function will update the linked histogram. So whenever we select data in our spatial distribution, we then want to update the linked histogram. And so this just is called update histogram, and it basically just rebins the data that gets selected. It takes the bounds as an input. These bounds are defined by the box in the box stream that we will show in a minute. So let's run that. So now, as before, we define our dynamic map, which includes the update histogram code. It defines a box stream. We have a few options set, and then we use Datashader to plot the full data set. So here we have now the same spatial distribution, right, ascension and declination of now the full 1.3 million set of data points. This is now data shaded, so you can see much clearer now regions of higher and lower density of sources in this region. There's clearly more here. And if and this is a histogram now of all the sources, a histogram in magnitude. So if I select a region, then it gets rebinned and rehistogrammed, rebinned, and the histogram gets redrawn, sorry. And so that's how you have a linked plot with interactive functionality. And that's it. Now I can delete the job so that the job doesn't hang around in the queue. And that ends the tutorial on how to do interactive analysis. There's a couple of exercises here for the learner. Again, same as before, HoloViews works with a wide range of plotting libraries, Plotly, Matplotlib. Feel free to change this and try something else. And another good exercise might be to write a different callback function in section 5.3. Now that you know how to plot millions of data points, try to do something else rather than just do a box selection on a spatial distribution and computer histogram. Try to do something more interesting. Okay, thank you. Thank you for listening. That's the end of the tutorial.
Yay, thank you. Round of applause for Leanne. That's cool stuff. So we can do some questions right away if anyone has a question on the material that was just presented. We can also, I'm going to share my screen. I'm going to take this screen share.
Do I have to unshare?
I think I can just take it because I'm the host.
Okay. Okay.
Yes. Yes, we want to go into breakouts now. One of our breakout sessions could be, oh, Leanne, do we have you for the second hour?
Yes, I can stick around.
Yeah, so one of our breakout rooms could be just to do those exercises to the learner with Leanne in in a breakout room for 6A or 6B. Everyone can try and make their own plot and then can show Leanne and get some advice on how to improve it. So that's one option for a breakout room. There is new truth data. So if people wanted to get together and work their way through Notebook 8 together and see what the truth data is, we could set up a breakout room for that. In the main room, as always, we'll have general Q&A. So any questions about, for example, like the new change to the tutorial notebooks directory being read-only, we can make a breakout room for that. And then the other usual breakout rooms on variability, large scale structure, synthetic sources, if people want those, you can do that as well. So at this moment, I'm just waiting for our delegates to tell me what kind of breakout room they want to have, either via the chat, or you can unmute and just say what you'd be interested in doing.